In the regret analysis, there are two parts. The first one is how many plays we have to do for suboptimal arms. So the explorations, the pure exploration part introduce regret. And the second one comes from the concentration inequality. From the concentration inequality, duration inequality analysis, we will have some additional regret. Okay. So for instance, let's go to the simple epsilon greedy approach. The epsilon greedy approach is very simple algorithm for multi-band setting, where we have explicit exploration part. We always have epsilon t probability. So with probability epsilon t at time t, we do not follow the best empirically best arm, but we randomly choose one of the k arms, just pure randomly for pure exploration. Okay, then with probability epsilon t, there is some regret will appear because epsilon t probability we do not play the best arm, we play suboptimal arm with very high probability. Okay, when there are k arms during this epsilon t selection, we uniformly randomly select one over arm among capital K arms. So only probability 1 over capital K is the probability we are playing with the best arm. With probability 1 minus 1 over K, we play suboptimal arm. So epsilon greedy for the exploration phase, we will have some additional regret because of this exploration, pure exploration. So this is one strategy how to choose epsilon value. There are a bunch of other approaches, other strategies to choose this epsilon t value, but we have to very carefully choose this epsilon t. When we increase this epsilon t, we will introduce additional regret, right? Why? Because in the regret analysis, we will add epsilon t all the time from t1 to capital T, and we will just consider this is a regret. Okay, sum of epsilon t, this is just a regret. So when you increase this part, then this regret upper bound increase as well. Okay, but when you decrease this part, there is another issue, the concentration inequality part. Okay, so in the concentration inequality part, what we do is we analyze the empirical average of the best sum and the empirical average of the any specific suboptimal arm I, and we figure out the probability mu hat star is less than or equal to mu hat I. So this is necessary condition arm I played instead of the best arm. Okay, so only if mu hat star is less than or equal to mu hat I can be played instead of the best arm. So additional regret can be occurred due to the arm I. So we have to analyze this one. So this one is another regret upper bound due to arm I, and we need to sum up the probability mu hat star less than or equal to mu hat I for all I is not equal to the best arm. And of course we have to do this for every time t. Okay, right. And for this, you can apply Hefting's inequality or Chernoff Hefting's inequality. And let's assume we apply Hefting's inequality. Then Hefting's inequality essentially, when we have Bernoulli distribution, that is 2 times, let's say this is the true mean was for this case, true mean was mu star, but this is we want to make a bound for this, right? So this term go to here with square, and with Bernoulli distribution, we always have 0 or 1, so the interval of random variable is bounded by length 1. So in the denominator there is n. So when n star for this, where n star is the number of plates with best sum, So for this case, you can easily bound the property, and okay, so there is n star square here, so canceled out. So essentially the property for this case is roughly exponential minus n star 2 times mu star minus mu I over 2 square. Alright? So this one will be very small because n star usually very high. But in this case, the n star maybe only depend on the epsilon t, sum of epsilon t, and sum of epsilon t is upper bounded by this. So sum of epsilon t control the number of exploration of suboptimal arm. So when this one is small, then here ni part for this concentration inequality is also very small. So we cannot make a very nice concentration inequality. This probability can be very high. But for the regret analysis, we also need to sum up this probability from T1 to capital T. So when this probability is bigger than 1 over T all the time, then the sum of this probability can grow up very rapidly. But here, we already have sum of epsilon t is proportional to log t. Indeed, 1 over t is enough. Okay? When we have 1 over t concentration inequality, roughly we can have log t additional regret due to this concentration inequality. When you target it to have 1 over t square concentration probability, then some of this probability will be just constants. This is also very nice, but to make 1 over t square concentration inequality, we need more observations because we need higher value inside exponential, right? So we may need to increase this epsilon t summation to guarantee more dense concentration, more well-concentrated result. If you want 1 over t cube, it's also fine. It is very nice result for this summation of this concentration probability. But again, this is not good news for this because to make 1 over t cube, you need to increase this part more. Okay? So there is trade-off between this concentration inequality and this exploration bound. So when you increase this exploration regret, you have to you can have less probability summation. On the other hand, if you decrease this epsilon exploration regret, you will have a higher value of this. And the sweet spot, I guess, the sweet spot is log t. Making log t regret for this, making log t regret for this is kind of sweet spot. Okay? Because to make constant regret from this, we cannot do better than log t times constant for this pure exploration part, because otherwise our concentration inequality cannot have constant regret. And when you have log t regress from this summation of probability, still you have to have log t explorations. Okay, so I believe log t is kind of sweet spot for designing epsilon greedy of epsilon t. Okay, optimistic algorithm is a little bit more tricky. The proof of optimistic algorithm, UCB algorithm, is more tricky. This is because in the UCB analysis here, the n, when you consider n is independent to mu hat value, so every observation is independent and the number of places of one specific arm is totally independent to the mu hat, then we can easily apply Hefting's inequality. But the problem of UCB algorithm is the number of places of each arm depend on mu hat value. Okay? So for this concentration inequality, UCB is less than or equal to some specific constant, we cannot simply apply Hefting's inequality or Chernoff Hefting's inequality because the number of places of arm A depend on the mu hat value. When mu hat value is high, then we will play the arm more than usual. When mu hat is very small at the initial point, then the number of play of such arm may be less than the usual. Okay, so the n value here maybe depend on mu hat. So we have to decouple mu hat and n value. That is the key part of the UCB type of algorithm. That is why we cannot directly apply epsilon greedy analysis to the UCB optimistic algorithm. Okay, so when you look at this proof, we use very interesting argument. Okay, so when arm A can be played instead of the first arm, the best arm, the arm A can be played only when UCB A is bigger than UCB 1, right? So let's say this is the event E, then there is some event set E. So here we want to find out upper bound of the probability of E. So we want to upper bound of this probability of this event. So to do that, we will define some superset, which consists of two different conditions. Either the UCB1 has very bad behavior, so this value is less than or equal to mu1 at time t. The second one is another case, UCB A, the arm A's UCB value is bigger than mu1. Okay. So this E condition has either the first part or the second part. Okay. Right? So every event instant satisfy either this or this. Since we are interested in the upper bound of this probability, we just need to define some superset very naively. It is fine that include this E event. And since we are using OR argument, this probability of E simply upper bounded by the probability of the first case plus the probability of the second case. Okay, so this is the this argument. Okay, And since the dependency, the number of plays, this N1T and NAT, and the UCB1T value and UCB8T value has some dependencies, we have to decouple the dependency between them. Okay, so what is the trick? Here, we can think there are, at each time t, there are t sequence of observations. There are t sequence of observation for arm1, and we can reveal a Bernoulli random variable for these t independent random variable, and then we can compute the probability. This one, either this one satisfies this UCB condition, either this one satisfies this UCB condition, either this one satisfies this UCB condition, and so on. If everyone satisfies this UCB condition, then with any N1T value, we can say that UCB8T has less than or equal to mu A value. Okay? And when we can say this is all event has probability 1 over T alpha, then the summation just simply T to the minus alpha plus 1. This is the trick. We can decouple N1T and UCB1T and NAT and UCB8T. So using that technique, we can upper bound this one by this. And the second one is still, this is not easy to analyze this. Okay. Still, it is not easy to analyze this, but first, what we do, first assume that n is greater than this. N is greater than this. Okay, just let's assume we have already this amount of random observation, and then as before, write down every sequence, and then see the observations. Independent observations. Okay, so just simply, no matter which NA value, we don't care. Just define mu hat A n is greater than or equal to mu star mu A over 2. If this satisfies, let's say we can play arm A. This is more mild condition compared to this. Because when n is bigger than this is necessary condition to have UCB80 is bigger than or equal to mu1. Right? So this is more mild condition. So again, this is upper bound of probability of this. And we say when we have satisfied this condition, we always play the arm A. And then the number of plays of arm A will increase one more time. Okay, so this summation simply upper bounds the summation of this indicator expectation. Right. And again here, when you define the UCB, when you define the upper confidence bound, we have this alpha constant. Okay, when you increase this alpha constant, what we can achieve more well-concentrated result for the best sum. We can have more less value for this one. But when you increase alpha, you have this more higher, this part. Why that happen? Basically, when you increase this alpha, the suboptimal arms can have more chance to be played because you increase the ranks of confidence bound, which increases the explorations. So when you increase alpha, you encourage the exploration, right? But at the same time, when you increase the alpha, you will have more well concentrated concentration inequality. So the decreasing speed of this property as n grows. So here we increase n to capital T, and when you increase alpha, the probability will more rapidly convert to zero. Okay, the conversion speed very related to the alpha value, and when you increase alpha, this probability very fastly converts to zero, so you will have more almost constant value for this summation when you increase alpha. But in the meantime, you have more exploration for here, this part. So you have to well control the alpha, and again, log t, we cannot escape the log t term. You cannot remove log t term for this exploration part. So the most tight case, okay, the best scenario for this summation, I believe, making this probability equal to 1 over, let's say, n. Make this probability proportional to 1 over n. Then the summation of this will have roughly log t. Okay? You can make a log t regret from here. Because we already log t term here, this additional log t doesn't care. Okay? This additional log t. Of course, you can make a constant term for here, and you can decrease this part more, but as long as you decrease this term will increase. Okay. KL UCB is the well-balanced scenario. So here we control the we set the upper confidence bound using this little bit more complicated rule. So here, using the empirical mean, we find the Q value that having this KL divergence with ham mu, and play with upper confidence bound defined by this. Then when you play infinitely many times, so when capital T go to infinity, what will happen? I believe this mu hat value in the end eventually go to mu a value, right? And we will control the NAT value so that this Q value a little bit less than mu star. Why? Because we play with the UCB value, and when capital T go to infinity, I believe mu star, because mu star, we play the best sum almost all the time. N star T, I think, also go to infinity, right? With a very, very high number of plays. So mu hat star is almost equal to mu star, and the UCB value as well. I think the UCB star, capital T, also almost close to mu star, because N star T is almost equal to capital T. So capital T, log T over capital T is almost 0. And to make 0 KL divergence, this Q value also should be mu star. So we know that the best arms, the upper confidence bound is mu star as well. So other arms will play it when the Q value becomes above the mu star value. and play it until the upper common bound a little bit below the mu star. So when you consider this fact, we will play arm A so that we have this bound. Then NAT can be bounded by log capital T KL divergence mu A mu star. Okay, so that is very smart way, and this is very good, especially capital T go to infinity. In the asymptotical area, capital T go to infinity, the regret function becomes almost optimal due to this very well balanced exploitation rule, and the rule comes from very well designed UCB value. Here we define the upper confidence bound so that the number of exploration make the probability mu hat is bigger than mu star is less than or equal to 1 over t. We really make this probability less than or equal to 1 over t, and then make the summation from 1 over t is log t, and log t is not important because we already have this term from the exploration.